Hello guys, and welcome back to my channel. This is the #1 channel for structural insight. Today I want to talk about axially loaded column with moment. So axially with moment. So what is moment? Moment in basics it means force times perpendicular distance. And in this case, the perpendicular distance is equal to eccentricity. And what is eccentricity? So eccentricity is the distance from the center of a column section to where the load is applied. Example, if you have a section like this, so this is a section of a column. So this is a section of a column. So this distance is what we call flange thickness, or T, like that. And this distance from here, this is D, capital D. And this distance is small d. And this one is small t. So if this is the center, so if this is the center, so the center is at this point, and this is the YY axis, and this is the XX axis. So as you can see, this load is at the center. So this load acting at the center, the eccentricity of this load is 0 because it is acting at the center of this section. But if we have a load at this point, so let's call this F. So this load is acting on the XX axis, but it is away from the center of this column. So this distance is what we call E, or eccentricity. So this will be, the load will be eccentrically from y-axis. So we call it a EY. Again, if we have a load at the y-axis, but away from the center, so this is F1 and this is F2. As you can see, this load is on the y-axis, but it is eccentrically away from the x-axis. So this distance is what we call EY. No, EX. So we want to see how we can uh, design if given a column like this having a load eccentrically applied on it. So let's see how we will tackle such a situation. So today I want to introduce you into axially loaded column with moment, and then I will solve two examples. I will tackle two examples, and if you have any question, you can ask through a comment section and I will be able to help. Or if you want me to help you, maybe you have a question and you want me to help you to solve it, you can take a picture of the question and send it to my email, which is odavig@gmail.com. So take a picture of your question and send your question to this email, and I will help you to solve the question. Now let's talk about the eccentricity for different connections. So this is beams and columns. So the first case is for a simple construction where the end connection are not intended to transmit significant bending moments, and the degree of eccentricity may be taken as follows. So this is the first case uh, uh, for a beam supported on a column cup plate. The load is taken as acting at the face of the column. So as you can see, this is a beam connected to a column, and between these two elements, we have the cup plates. So this is the column, and this is the beam, and in between here we have the cup plate. So E is taken as D over 2. So E is equal to D over 2. So let's go to the second case. So B, we have where the beam are connected by simple connection to the face of a column. The load should be taken as acting 100 millimeters from the face of the column. So we have two different connections. The first connection is when the column section or the universal column is in this form. So we have the y axis and we have the x axis. So this is the column and this is the beam. The beam is connected to a column. So the load is acting 100 millimeters from the face of the column. So to obtain EY, whereby the load is acting, you will take T over 2. So this is, we have said this is the T. So T over 2 plus 100. And for another case where this column is now, the column has now been turned like this, as you can see. So like it has been rotated into this format. So this will be the x axis and this will be the y axis. No, this is the y axis and this is the x axis. So this is the column and this is the beam. So the beam is connected to a column and it is carrying a load at this point. So the load is 100 meters from the face of this column. So to get EX, you'll take D over 2 plus 100, whereby D over 2, as I have said, is this distance. So D over 2 is this distance, like that. So let's proceed to the last case. So the last case is when a rough truss is supported on a column cap plate and the connection cannot develop significant moment. So the eccentricity may be neglected. As you can see, this is the connection. So the eccentricity is equal to 0. Example number 1. So example number one, the question is on the board and it reads, check the adequacy of a 203 by 203 by 60 kilogram per meter universal column in grade 43 steel to support the ultimate load shown below. The column is pinned at one end and fixed at the other end over a length of 6 meters. So before we begin solving this question, let's capture the most important information on this column. So the column is pinned. It is pinned at one end and fixed at the other end. So the length of the column is 6 meters. And the section of the column is 203 by 203 by 60 kilogram per meter. And the strength is grade 43. So grade 43. Again, let's draw the section here. So this is YY axis. And this is XX. So the load at the center is 100 kilonewton. And here we have 100 again 100 kilonewton, again 100 kilonewton. So having done so, I can clean here to create space for our calculation. So solution. So the first thing to do is to go to the table of universal column and obtain properties for this size you have been given, so that the properties will help you to check the adequacy of this section. So properties, under properties, so for the properties, you will obtain D T, capital T, small t, then the area, which is AG. We have the radius of gyration, R, XX, R, YY. We have D over T. We also have B over capital T. And then, of course, we have Z, YY. And then SX, the plastic modulus. And then IXX. So let's go to the table and obtain these properties. I will show you the table. So this is the table for universal column. Just check where my cursor is. So we have 203 by 203 by 60. So you will come and obtain all relevant properties together with their values. As you can see, we have 209.6, that is for capital D, and then we proceed to small t, which is 9.3 millimeter, and then capital T, which is 14.2, and so on and so on. So you will obtain all the values for that. And then we have the plastic modulus. For the major axis, we have 652 centimeter cube. And then we have the elastic modulus. So for elastic modulus, you will obtain elastic modulus for YY, which is 199. And then we have the radius of gyration for XX and YY, 8.96 and 5.19. So you will obtain all those relevant properties together with their values. So let me write it on the board. I hope you have now seen how to obtain or how to read the table. So we have D as 209.6 millimeter. Capital T is 14.2 millimeter. Small t is 9.4 millimeter. Be keen on the units because we have millimeter and centimeters. So area is 76.4 centimeter to power of 3. And then we have our XX, radius of gyration on the XX axis, 8.96 centimeter. And then our YY, 5.20 centimeters. And then you have D over T, D over small t, this is 17.1. We have B over capital T, this is 7.25. We have the YY, this is 201 centimeter cubed. We have the plastic modulus, 656 centimeter to power of 3. No need for IXX. So after doing so, the next thing to do is to classify the strengths. But before I classify the strengths, allow me to capture this on this column. So D is equal to 209.6 millimeter. Capital T is equal to 14.2 millimeter. Small t is equal to 9.4 millimeter, area is equal to 76.4 centimeter to power of 3 or cubed. And then we have ZYY is equal to 201 centimeter cubed. Plastic modulus is equal to 656 centimeter cubed. RXX, radius of gyration on the XX axis, 8.96 centimeters. And then YY is equal to 5.20 centimeters. D over T, small t, 17.1. B over capital T, 7.25, like that. So strength classification. Strength so there is a table for strength classification. I won't talk more about this. You already have the table. So for strength classification, we always use capital T, which is 14.2 millimeter. So 14.2 is less than 16 millimeter. Therefore, Py is equal to 275 Newton per millimeter square. 275 Newton per millimeter square. Then after that, we'll obtain this, which is equal to square root of 275 over Py. So this one is equal to 275 over 275, which is equal to 1, like that. So after strength classification, we will proceed to what we call as section classification. So section classification. Again, I gave you a table which guides you on how to classify the section. So if you are not, or if you have forgotten, you can visit the introduction to steel design. You will get this table there. Or you can check one of my examples concerning beam design. So for section classification, we have the flange. So the flange, for the flange, we always use B over capital T, which is equal to 7.25. And this 7.25, from the table, it is less than 9.0 E. So 7.25 is less than 9.0 times 1. So it is true, 7.25 is less than 9.0 times 1. Therefore, the flange is class 1. Plastic. We proceed to the web. So for the web, we always use this, we always use D over T. So this is the capital D over T. So this one is 17.1. And from the table provided by BS5950, 17.1 is less than 80 E. So if you multiply 80 by 1, it will be true that 17.1 is less than 80 times 1. So therefore, the web is class 1 plastic. The web is class 1 plastic. So section 2 or 3, section 2 or 3 by 2 or 3 by 60 kilogram per meter is class 1 plastic. So we are already done with the classification. So we now proceed to the design load. We now proceed to the design load. And remember, this is small b, not capital B. Small b over T. So remember, Py is equal to 275 Newton per millimeter square, like that. So the design load it will be, so F is equal to 100 plus 100 plus 100. So this is in kilonewton. So which imply F is equal to 300 kilonewton. So that is the design load. And then the effective length. So the effective length is equal to, for the column which is pinned at one end and fixed at another end, is given by 0.85 times L, where L is the overall length of the column. So this one is equal to 0.85 times length, which is 6 times 1,000. We are converting it from meters to millimeter. So this one is equal to 51. This one is equal to 5100 millimeter. So LE is equal to 5100 millimeter, like that. So we now proceed to the slenderness ratio. So slenderness ratio, it is symbolized by this. This is the lambda. So we'll begin by the slenderness ratio for the x-axis. For the x-axis, it will be LE over R XX. So this one is equal to 5100 all over RXX, which is 8.96. Remember, 8.96 is in centimeter, and this one is in millimeter. So you will multiply this by 10 so that you can work with uniform units. So this one is millimeter. If you multiply by 10, the numerator and the denominator will be in millimeter. So your answer is 56 So this one is equal to 56.92, which is less than 180. Why is it, or why must it be less than 180? Because we are designing for a dead load and impost. So for the dead load and impost, it is limited to 180. Then we proceed to slenderness ratio for YY, which is equal to LE over RYY. So LE remains the same, 5100 all over RYY, which is 5.20 centimeter. So you will multiply by 10 to make it millimeter. So this one will give us 98.02, 98.02, which is less than 180 for dead and impost. Therefore, okay. After calculating the slenderness ratio, we now proceed to buckling about x-axis so that we can obtain the PC. So the PC is the compressive strength. The PC is the compressive strength. So let me write the slenderness ratio here. Xx is equal to 56.92. Yy is equal to 98.02, like that. So this one is over 10 times 10, not 0, times 10. Sorry for that. Also, something important to capture on this column is F is equal to 300, because we want to check if the section will sustain 300 kilonewton or not. So now you are proceeding to what we call the PC. So the PC is the compressive strength. So we will begin by buckling about x-axis. So buckling about x-axis. And for this, we will use the slenderness ratio, which is 56.92 and PY, which is equal to 275, to enter table 27B or 24B, like that. So let's go to the table. Let me show you the table. So before I can show you the table, as maybe someone is asking himself or herself, why am I going to, or what is guiding me to go to table 27B or 24B? We also have 27C or 24C. So what is guiding me is this table. I hope you have this information. Is this table. So it's the flange thickness, which is up to 40 millimeter for buckling axis. For x axis we will use table 27B, and for y axis we will use 27C. And over 40 millimeters, we will use 27C for XX axis and 27D for YY axis. So that is the guideline. So always remember this part. So let's now proceed to the table. So this is the table. This is the table. So our slenderness ratio is 56.92 and our PY is 275. So for this column, see where the cursor is. This is for slenderness ratio and this is for the strength, S275. And for S275, you have 235, 245, 255, 265, and 275. Since our slenderness ratio is 56.92, so we'll check if it is available on this column. So it is not available. So we have 56 and 58. So we will go for a value which is slightly lower than the slenderness ratio we have, and also for a slightly higher value for the slenderness ratio we have, which is 56.92. So for our case, we will go for 54 and 56. And then we will come to this, we'll come to 275. So for 275, we have 230. So we have 54 and 275. The value there is 230. And for 58 and 275, the value there is 227. So see where the cursor is. After doing so, you'll interpolate so that you can get 56.92, like that. So that is how you read that table. Sorry, I have made a very small mistake. So we have 56 and 58. So for 56, we have 227. See where the cursor is. And for 58, we have 224. After that, we'll interpolate and get the value for 56.92. So we have the slenderness ratio, and we have 275. So here you have 56 corresponding to 227, and then we have our value here, which is 56.92 to x, and then we have 58 corresponding to 224. At this juncture, I know you know how to do the interpolation. So just get the difference between these two. So this is 0.92, and also between 58 and 56 is 2. Between this, you will get 3, and this one, we assume this is x. Then 2, you do the comparison to get the value of x. 2 over 3 is equal to 0.92 over x. You cross multiply, which imply x is equal to 3 times 0.92 divided by 2. So this is 1.38. 1.38. So PC, this is for x is equal to 227 minus 1.38. So which is equal to 227 minus answer. So this is 225.62 Newton per millimeter square. So this is PC for XX axis. And then you go for YY axis. So before I rub, come here. Let me write it here. PC. PC for XX axis. XX 256.62 Newton per millimeter square. Then I will rub here. So we will repeat the same procedure for the YY axis. So buckling about YY axis. So for you to enter into table 27C, you need slenderness ratio about YY axis, which is 98.02, and PY, which is equal to 275. Again, we'll go to the table and obtain the PC for YY axis. So this is the table 27C or 24C. So we have the slenderness ratio column and the PY column. So for our slenderness ratio is 98.02. So check where my cursor is. So that is the column that will guide us. So that is the column for slenderness ratio. So we'll go up to where 98 is. So you have 98. As you can see, we have 98 and there is no 98.02. So we'll interpolate. So you'll take a value which is slightly lower than 98.02, which is 98, and the one which is slightly higher than 98, which is 100. And for 98, we'll go up to where 275 is. So this is the last column. We have 129, and for 100 is 125. And then you do the interpolation to obtain a PC for 98.02, as shown on the board. So we have 98. We have the slenderness ratio, and then PY. So 98. So for 98, we have 129. And then we have 98.02. This is X. And then 100. For 100, we have 125. Like that. Then we do the interpolation to obtain the one for 98.02. So get the difference between these two. So this is 0.02. And then for this is 2. This is 4. Let's say that is X. So 2 over 4 is equal to 0.02 over X, which imply X is equal to you cross multiply 4 times 0.02, then divided by 2. So this is 0.04. 0.04. So the PC for YY is equal to 129 minus 0.04, which will be 129 minus 0.04. So this is 128.96 Newton per millimeter square. So you'll come here and say PC is equal to, this is for YY, for YY is equal to 128.96 Newton per millimeter square, like that. So having done so, you will use a PC which is lesser between the two. So you'll say use PC which is lesser between the two. So this PC is for y-axis. So this one is equal to 128.96 Newton per millimeter square. This one. Like that. Then after that, we now proceed to compressive resistance. Compressive resistance. So the compressive resistance, which is capital PC, is equal to AG PC. So this one is equal to, we have our AG here. This is 76. Cross-section area is 76.4. So 76.4 is in centimeter square. This should be square. 76.4 centimeter square. So you will multiply by 10 to power of 2. So we are changing it from centimeter square to millimeter square times 128.96. So this is PC, 128.96. And because our answer will be in kilonewton, in Newton, so you multiply by 10 to power of -3 to get the answer in kilonewton. So 76.4 times 10 to power of 2 times 128.96 times 10 to power of -3. So this is 985.25. 985.25 kilonewton. So this 985.25 is greater than 300 kilonewton. So this is the applied force. So this is the applied force, which was F. So you will say, therefore, okay, therefore, the section is okay. The section is okay. Then after doing so, we'll now proceed to the stability, to check the stability of this section. So let's proceed. So we know that for stability, F over PC AG plus MX over MB plus MY over PY ZY must be less than or equal to 1. So we have F, we have PC AG, but we don't have MX. So for us to find the MX, we start calculating the eccentricity. So eccentricity, let's start with eccentricity X. So eccentricity X is equal to, so this load here will give us eccentricity X. So this is EX. And remember we said the load is acting 100 millimeters from the face of the column. So this is 100. And this one, this distance is D over 2. So EX is equal to D over 2 plus 100. So this one is equal to, our D over 2 is 209.6 over 2 plus 100. So this one is equal to 204.8 millimeter. And then we have the EY. So EY is equal to T over 2 plus 100. So this load here, it is eccentrically from YY axis. So this is EY. So and remember this distance from here to here is 100. And this one is T over 2. So we already have T. So T is 9.4 all over 2 plus 100. So this one is equal to 104.7 millimeter, like that. So MX, now this one is equal to, so MX will be 100 times 204.8, then times 10 raised to power negative 3. Why 10 raised to power negative 3? Because this is in millimeter and we want our answer in kilonewton meter. So you'll multiply by 10 raised to power negative 3 because 1 meters is equal to 1,000 millimeter. So this one is equal to, if you multiply, you'll get 20.48 kilonewton meter. Let's go to MY. So MY will be 100 times EY, which is 104.7, again times 10 raised to power negative 3. So MY is this one, 100 times EY, and then MX is this one, 100 times EX. So this one is equal to 10.47 kilonewton meter. So the buckling resistance We now proceed to buckling. Buckling resistance. So buckling resistance is given by 0.5 L over Ry. So this one is equal to 0.5 times L. L is 6 meters times 6 meters times 1,000. We make it millimeter over Ry. So Ry is here 5.2. 5.2 times 10. We make it centimeter millimeter, from centimeter to millimeter. So you will multiply by 10 like that. So you will get 57.69. So this one is equal to 57.69 like that. Then PB will be given by, so allow me to capture the moment mx and my on this column. So we have mx is equal to 20.48 kilonewton meter, and my is equal to 10.47 kilonewton meter like that. So PB, which is the bending strength, PB is given in table 11 using the following, which is 57.69 and py. So you'll need this and py so that you can obtain the bending strength, which is PB, in table 11. So for us to calculate the PB, which is the bending stress, as I have said, we'll use table 11. Of course, it's not 11, but table 16. And we need this value, which is 57.69, and py, which is the strength of this steel, which is 275 Newton per millimeter square. So I will show you the table. So this is the table. This is the table. As you can see, this is the table. So we'll go for 57.69. So 57.69. So as you can see, that this column is for the value we have calculated, which is 57.69. As you can see, there is no available value for 57.69 on this column. So we'll again do the interpolation. So for the interpolation, we'll go for a value which is slightly lower than 57.69. So this will be 57 will be 60, and again we'll go for a value which is slightly higher than 57.69. So this is 60, so 55 and 60, and then we'll come to this column, which is 275, py of 275. So we have 226 and 213. You can see where the cursor is. 55 is corresponding to 226, and 213 for 60. And then we'll do the interpolation. So we have this one, and then 275. So we have 55 corresponding to 226. And then our value here is 57, 57 point 57.69 corresponding to x, then 60 corresponding to 213. Again, we'll do the difference. So 57.69 minus 55, this is 2.69. Again, these two, 60 minus 55, this is 5. So 213 minus 226, so this is 13. And here is x. Again, we'll do the comparison. 5 over 13 is equal to 2.69 over x. You cross multiply, which imply x is equal to 13 times 2.69 divided by 5. So this is 6.994. So the PB is equal to 226 minus 6.994. So this one will be 226 minus answer. This is 219.006. This is 219.006. So you can say 219.01 like that. So after doing so, we will now calculate the MB. So MB, this one. So let me show you. So MB is equal to PB SX, whereby PB is this value and SX is the plastic modulus, which is 656 centimeter cubed. So this one will be, this one is equal to, PB is 219.01 times 656 times 10 to power of negative 3. No, to power of 3, because we want to change this centimeter cubic to millimeter cubic. So 1 centimeter is equal to 10 millimeter. What about 10 to raised power 3? So it will be 10 raised power 3 times 10 to power of negative 6. Why 10 to power of negative 6? Because if we work on this, we will get our answer in Newton millimeter, but we want our answer to be in kilonewton meter. So you'll multiply by 10 to the power of -6. So this one is equal to 143.67 kilonewton meter, like that. So after having done so, we can now check for stability by inserting the values in this question, and we will see if it will be less than 1 or equal to 1. So let's see. Our F is 300. Our PC times AG, we have already calculated that, and our answer was or is 985.25 plus MX. MX is here 20.48 all over MB. We already have MB as 143.67 plus MY. MY is here 10.47 all over PY. PY is 275 times ZY. ZY is here 201, like that. So it must be less or equal to 1, as you have seen in the question. So let's check and see. So you have 300 over 985.25 plus 20.48 all over 143.67 plus 10.47 over 275 times 201. So it's 0.44. So it is okay. So 0.45, which is less than 1. Therefore, section is okay. Section is okay. And our question ends there. So if you are doing your exam, I know you may stuck on the way. So make sure at least you have done 3/4 of such a question, because this question is 20 marks. So if it is 20 marks, make sure you have scored at least 15 and above. You may not be able to reach here, but at least do something that will earn you marks. And that marks should not be less than 15 for you to pass this paper. I'm going to example number 2. So example number 2, this is example number 2. Design a suitable grade 43 steel universal column to support the ultimate load shown below. The column is pinned at one end and fixed at the other end. The overall length is equal to 6 meters, and this question is 20 marks. As you can see, this is the section of a column. It is carrying an axial load of 400 kilonewton, and it is carrying another load on the YY axis, which is away from the center, and this is 300 kilonewton, another one 200 kilonewton. Another one on the YY axis, again away from the center, This is 250 kilonewton and 150 kilonewton. So let's see how you can solve such a question. And before I begin, let me capture the most important information in this column so that I can rub here and create space for our calculation. So the grade of the steel, so grade is equal to 43. And then the column is pinned at one end and fixed at the other end. And the length is 6 meters. Of course, I draw this here. I hope you can see clearly. So this is what is here. So I want to rub here so that you can continue with our question. So a solution. So the first thing to do is to determine the applied force. So determine F. So F is given by, so F, the first thing is to note about F. So F is the total applied force. Total applied force. And F is equal to, you will take F is equal to 200 plus 400 plus 250 plus 150. So F is equal to 200 plus, this is 200 plus 400, this one, plus 150, 150 is here, plus 250, this one, plus 300, like that. So this is in kilo Newton. So the total F, or the total force is equal to 1300 kilo Newton. And then after that, you will proceed to effective length. So effective length, LE, is equal to, because this column is pinned at one end and fixed at the other end, so the formula for LE is 0.85L. So L is the overall length. So this one will be 0.85 times 6 meters times 1,000. You change from meters to millimeter, and this one will be, 5100 millimeter. 5100 millimeter, like that. So you can come here and say F is equal to 1300 kilonewton, then LE is equal to 5100 millimeter, like that. And then we'll choose a trial section. So choose a trial section. Choose a trial section. For you to choose a trial section, for this case, we don't have the moment, because you remember for the beams, what used to guide us is the plastic modulus. This is the plastic modulus, which must be greater than m over py. But for this case, we don't have m. There is no m. So what will guide you is the flange thickness. So you can say use T. This is the flange thickness to be less than 40 millimeter. So that when you go to the table of a universal column, you will select a trial section which has flange thickness of less than 40 millimeter. So you can choose any. You can choose any value, so long as it is less than 40 millimeters. It can be 16 point whatever, 25, 35, like so on. So what matters is if the section will pass or not. And for the section to pass, you have to check the parameters given in the code, which is BS5950. So if it passes, then that section will be used to design a column with a total applied force of 1300 kilonewton. But if it fails, you will again go back and select another section and try if it will pass or fail. So it's a trial process with different sections until it passes the parameters given in BS5950. So let's go to the table. Let's go to the table. So this is the table. As you can see where the cursor is, so that column is for capital T, which is the flange thickness. So we have said we want to use the T as less than 40 millimeter. So for this case, I want to use T as 15.4 millimeter. Again, for someone who is more experienced in this design of T to BS59, he can easily guess the section to be used depending on the total applied force. But for you as a student, you just choose a trial section and check if it will pass or fail. If it fails, you just write a statement by saying that not okay, try another section. And you leave it at that point and you continue with the other design consideration. But for someone who is practicing, you will go back and choose another section and start the process of checking. So let's choose T as 15.4. So this is 15.4. So the section for 15.4 is 305. Just check where my cursor is 305 by 305 by 97 kilogram per meter. And then you will come and write all the properties. That is for D. Example D, which is 307.8, small t, which is 9.9, radius of gyration, and so on and so on, up to the last one, which is area, and the area is 123. So let's write the properties and the section on the board. So you will say try, because we are not sure, try 305 by 305 by 97 kilogram per meter. And then after selecting this section, you'll write all the properties, and these properties will help you to examine the section if it will pass or fail. So you have D, the D is 307.8. We have capital T, which is 15.4 millimeter. So this is also in millimeter. We have small t. Small t is 9.9 millimeter. We have the radius of gyration about x axis. This is 13.4 centimeter. When you are writing this, or you are taking these values from the table, be keen on the units, because we have others in millimeter and others in centimeter. So RYY, the radius of gyration about YY axis, 7.69 centimeter. And then you have the aerial, which is AG, is equal to 123 centimeter square. We have D over T is equal to 24.9. B over capital T is equal to 9.91. ZY is equal to 477 centimeter cubic. A plastic modulus is equal to 1590 centimeter cubic. So I want again to write these properties on this column so that you can rub here to create space for our calculation. So you have said try 305 by 305 by 97 kilogram per meter. As you can see, everything has been captured on this column. So allow me to clean here. Now, let's now proceed to what we call a strength classification. So strength classification. I will keep on saying that for strength classification, there is a table provided by BS5950, which guides you on how to classify the strengths. So the table is in my first video, which is introduction, or you can check one of the example in design of beam. So for strength classification, we always use flange thickness as a guideline. For this case, it is 15.4 millimeter. And this 15.4 is less than 16 millimeter. Therefore, Py is equal to 275 Newton per millimeter square. You can as well come here and say Py is equal to 275 Newton per millimeter square. After classifying the strength, we again classify the section. And before we classify the section, let's obtain this value, 275 over Py. So this one is equal to 275 over 275, which is equal to 1. And then we proceed to section classification. Again, for section classification, a table has been provided to guide you on how to classify the section of such a column. So we'll begin by the flange. So for flange, we use B over T, the ratio of B over T, which is equal to 9.91. And this one is less than 9.0, like that. So it is true 9.91 is less than 9.0 times 1, because the value for this is 1. So therefore, class 1 plastic. So the flange is class 1 plastic. We proceed to the web. So for web, we always use this ratio, B over T, small d over T, which is equal to 24.9. And from the table, it is clearly that it is less than 80 E. So it is true 24.9 is less than 80 times 1, because the value for this is 1. It is here. Therefore, the web is class 1 plastic, like that. And then you will say section 305 by 305 by 97 kilogram per meter is class 1 plastic, like that. Is class 1 plastic. So then after that, we'll come to slenderness ratio. Slenderness ratio. Allow me to clean here. So slenderness ratio which is symbolized by lambda. So for slenderness ratio, we will start by slenderness ratio about x-axis, which is equal to LE all over RXX. So LE, we have it here, 5100 over RXX, which is 13.4 centimeter. So you'll multiply by 10 to make it millimeter. So this is, if you punch your calculator, you will get 38. So this one is equal to 38.06 which is less than 180, because we are designing only for a dead and imposed load and not for a wind. So therefore, okay. And then we will also calculate the slenderness ratio for YY axis, which is equal to LE all over R YY. So the LE remains the same, 5100 all over RYY, which is 7.69 times 10. So we are changing it from centimeter to millimeter. So this one will give us 66.32. 66.32. Again, it is less than 180. Therefore, okay, it must be less than 180 when designing for a wind and no, when designing for a dead plus imposed load. After that, let me write it here, is equals to 38.06, and then YY is equal to 66.32, like that. After that, we proceed to compressive strength. Compressive strength, which is PC. Compressive strength. So the compressive strength, we will start PC about XX axis. PC about XX axis. And this one will use table, use table 27B or 24B. So this is the buckling about XX axis. Buckling about XX axis. So I think you know how to read this table, because I've already shown you in example 1. Nevertheless, I will show you again, but I will be as fast as possible. So let's go to the table, and for you to enter this table, you will need the slenderness ratio for the XX axis, which is 38.06, and PY, which is 275 Newton per millimeter square. So let me take you to the table very fast. So this is the table. This is the table. As you can see, our value is 38.06. So this is the column for slenderness ratio. So 38.06 is not available amongst what we have here. So what we'll do, pick a lower value which is slightly lower value than 38.06. So that is 35, and come to 275. So this is 256. And then for 40, this is 250. And then you will interpolate to get the value for 38.06 as shown on the board. So we have the slenderness ratio and 275. So we have 35, 256, 38.06 to X. And then we have 40, and this is 250. Then you get the difference between these two. So 38.06 minus 35, this is 3.06. And then again, this one, 40 minus 35, this is 5. Also get the difference between these two. So 256 minus 250, this is 6. And this one here, we assume is x. To obtain x, do the comparison. 5 over 6 is equal to 3.06 over x, which imply x is equal to cross multiply and obtain the value of x. So this is equal to 6 times 3.06 divided by 5. So this one is equal to 3.672. So again, you will say PC about xx is equal to 256 minus 3.672, which is equal to 256 minus answer 252.328 Newton per millimeter square. So this is PC. This is PC for about xx axis. So let's obtain again a PC about yy axis. About yy axis. So for this, we'll use table 27C or 24C. The procedure is the same. The procedure is the same. So for this case, I won't show you how to do it because you already know how to read these values from the table. So let me just do the interpolation here. So we have and 275. So we have 66 corresponding to 189. And then our value here, which is 66.32 corresponding to x. Then we have 68 corresponding to 185. Then you get the difference. This is 0.32. And this one, this is 2. So this one is 4. 189 minus 185. And then this one is x. So again, we'll do the comparison. 2 over 4 is equal to 0.32 over x, which imply x is equal to 0.32. 0.32. So PC about yy axis is equal to 189 minus 0.32. So this one is equal to 188.68 Newton per millimeter square. So after that, we'll say choose a PC which is lesser which is lesser for the two. So the PC is equal to 188.68 Newton per millimeter square, because this 188 is lesser amongst these two. So it's lesser if you compare this and this. So this one is lesser. So after calculating PC, we now proceed ahead and calculate the compressive strength. The compressive strength. So the compressive strength is given by this formula, whereby this is the compressive strength, the cross-section area, and PC is the compressive strength. This is the compressive resistance, cross-section area, and compressive strength. So this one is equal to AG is 123 times 10 raised power 2, because we are changing from centimeter square to millimeter square, times PC 188.68 times 10 to power of negative 3 times 10 to power of negative 3. Why? Because we want our answer in kilonewton. So if we don't multiply by 10 raised to power negative 3, our answer will be in Newton. So if you carry out the operation, you will get PC as 20.764 kilonewton. Compare this PC with applied load or applied force. So the applied force is 1300 kilonewton. So you will say F is less than PC. So F is 1300 is less than 20.764 kilonewton. Therefore, okay. Therefore, section okay. After doing so, we now proceed to eccentricity. Eccentricity EX and EY. EX and EY. So let's now proceed to eccentricity. This is our column section. Let me draw it here so that you can see it clearly. So this is YY. We have loading at this point, which is 300 kilonewton. Another loading here, 150. Another loading here, 250. Another loading here, 200. And axial load at the center, which is 400. So eccentricity, why are we calculating or why are we determining the value of eccentricity? Because this value will help us to calculate the moment about XX and YY axis. So EY, no, let's begin with EX. So EX will be this distance, because this is the YY axis and this is the XX axis. So eccentricity means away from the center. So this is the center. So this is the distance. This is the distance, like that. And remember, we said that this load is 100 meters from the face of the column. So this is 100. So we are remaining with this distance from here to the face of the column. This. So this one is given by D all over 2. So EX is equal to D over 2 plus 100. So this one is equal to D is here 307.8 over 2 plus 100. So this one is equal to 253.90 millimeter. Let's proceed to EY. So EY, this is the YY axis. So the EY is this distance. So this is the EY. And this distance, as we have said, from the face of the column to where the load is active is 100. So we are remaining with this distance. So this one will be T, small t over 2 plus 100. So T is here 9.9 over 2 plus 100. So this one is equal to 104.95 millimeter. So remember, this distance is also the same for the other loading which is away from the center of the column. Like for example, this one. So this distance is EY. So it's the same as this one we have calculated. And also this one from here to the center is the same as EX, 253.90. I hope you have understood. So let's now calculate the moment. So moments, we will begin by mx. Mx is given by force times eccentricity, or times Ex, like that. So we will come here So EX is this distance. So this is the EX. So we'll get the difference of this loading on the YY axis. So we'll take 300 minus 200, then you multiply by EX, which is 253.90. Of course, this is in millimeter, so you will multiply by 10 to power of negative 3 to make it meters. So I have said this because we want mx, we'll take the loading. You will get the difference of the loading on YY axis. As you can see, we have 300 and 200. So the difference is 300 minus 200. Then you multiply by EX, which is 253.90. So this one is equal to 25.39 kilonewton meter. We proceed to MY. Again, MY, it will be force times EY. So the force is this distance. No, the force is the difference between loading on the YY axis, which is 250, minus 150, then times EY, which is 104.95, then multiply by 10 to the power of negative 3 to make it millimeter. Meters, not millimeter. So this is power of negative 3. So if you carry out the operation, you will get 10.495 kilonewton meter. So we have already calculated the moment My and moment Mx. Buckling resistance, which is Mb. So before we proceed to buckling resistance, let's capture this moment on this column. So Mx is equal to 25.39 kilonewton meter, and then My is equal to 10.49 kilonewton meter, like that. So we now proceed to buckling resistance, which is Mb. So Mb, which is given by this formula, PBSX. So this Sx is the plastic modulus, and this one is the bending strength. So we will begin by PB, bending strength. So for us to calculate the PB, which is the bending strength, we need these values. We need this value, which is given by 0.5 L over Ry. So this one is equal to 0.5 times length, which is 6, then times 1000, change it from meter to millimeter, then Ry 7.69. Ry is here. This is the radius of gyration about y axis. So 6.9 times 10, you change it from centimeter to millimeter. So this one will give you 39.01. You also need this value, Py, which is equal to 275 Newton per millimeter square. So having these two values, we'll proceed to table 16 and obtain PB. So I will show you how to obtain PB from table 16. So this is table 16. As you can see, we have a column for this slenderness ratio, and then for the grade, steel grade and design strength Py, Newton per millimeter square. So our value is 39.01, and this is for slenderness, and Py is 275. So you will come here and check if 39.01 is available on this column. Unfortunately, 39.01 is not available. So you will go for a value which is slightly lower than that, which is 35, and go along up to 275. So you have 273, and then go for a value which is slightly higher than that. So we have 40, and up to 275 is 262. And then you'll carry out the interpolation. So we have 275. So we have 35 corresponding to 273, and then 39.01 x, and then 40, 262. So get the difference. So this is 39.01 minus 35. This is 4.01. And then also this is 5. This one, 262 minus 273. This is 11. And this is x. So just to do the comparison, to obtain the value of x, 5 over 11 is equal to 4.01 all over x, which imply x is equal to cross multiply 11 times 4.01, then divided by 5. So x is equal to 8.822. Therefore, PB is equal to 273 minus 8.822, which is equal to 264.178 Newton per millimeter square. Newton per millimeter square. So to obtain MB, MB, which is the buckling resistance, so MB is equal to PBSX. So this one is equal to PB is 264.178 times SX, which is the plastic modulus, 1590, because it is in centimeter cubic, you will change it to millimeter cubic. So you will multiply by, no, you will change it to millimeter cubic. So you will multiply by 10 to power of 3, then times, because our answer will be in Newton millimeter, and we want our answer in kilonewton meter, you will multiply by 10 to power of -6, so that you can get your answer in kilonewton meters. So if you carry out the operation, you will get this one is equal to for 20.04 kilonewton meter. So this is MB. You can come here and say MB is equal to 420.04 kilonewton meter. Like that. After that, we proceed to for stability check. So stability check. So for stability check, we'll apply this formula F over AGPC plus MX MB plus MY PY ZY must be less or equal to 1. So our applied force, which is F, is here, 1300 over, we already have this value, we have already calculated this value, and it is 23. It is 20.764. So this is the compression resistance plus MX. MX is here 25.39 over MB. MB is here for 20.04 plus MY. Again, MY is here 10.49 all over PYZY. So PY is 275 and ZY is 477. It is here 477. So it must be less or equal to 1. So if you carry out the operation, you will get 0.62, which is less than 1. Therefore, okay. So you will say section 305 by 305 by 97 kilogram per meter is okay. And the question ends there. So that is all about column design, which supports axial load and moment. And I think that is the end of that subtopic. Unless if you have any question from past paper, you can let me know through a comment section, or you can take a photo of that question and send me to my email. I gave the email in the beginning of the session. So send your question to that email and I will be able to help where possible. So if you have not subscribed to this channel, subscribe and be a member. Hit that notification bell so that you may be the first person to be notified when I upload a video. So in my next session, I will talk about the cased column design, and probably it will take like two days and I will be done with that. So thank you for your time and we meet again in my next session.